Okay, close your eyes for a second. I want you to picture a military shooting range. You've seen them in movies if you haven't been to one.
Hmm.
You're standing in your lane looking down this uh, perfectly manicured strip of dirt, and then pop a green plastic silhouette just flips up.
The classic pop-up target. Yeah, a
Yeah,
staple of military life.
exactly. You shoot it, it flips down.
Yeah.
Or, maybe if the range is a little fancier, the target slides left to right on a rusty rail.
Kind of like a duck in a carnival game.
It's totally like a carnival game. And it's fine for learning basics, sure,
Mm.
but it is so incredibly predictable. You know exactly where it's coming from.
And that predictability is precisely what the U.S. Army is trying to kill. Because in the real world, threats don't move on rails. They don't wait for you to be ready.
And they definitely don't just sit there waiting to be shot.
Not at all.
And that's really the big shift we're digging into today. We're looking at a document that basically outlines the end of that whole carnival game era of training. The Army has issued a massive challenge to the tech world. They want robots.
Specifically, Next Generation Trackless Targets.
NGTT.
Right. And just to be clear, we're not talking about like a remote-controlled car with a balloon tied to it. We are analyzing a call for solutions and this incredibly detailed performance specification document.
And it comes from PEO-SDOI.
PEO-SDI, the Program Executive Office for Simulation, Training, and Instrumentation. It's a mouthful.
It is. But they're the people whose job it is to make training feel real. And this document isn't just a wish list. It has a deadline.
A very, very tight one.
Yeah, we're recording this on January 30th, 2026. And the deadline for companies to get their ideas in is February 12th, 2026.
That is less than 2 weeks. It's a sprint.
So why so fast?
It's a procurement method called a commercial solutions opening, or CSO. We can get into the business side later, but the Army is basically saying we need this now, and we think someone in the commercial world might already have 90% of the answer.
Someone building, what, delivery bots or something?
Exactly. Agricultural robots, delivery bots, they think the solution is already out there.
The mission is stated very clearly. It's about increasing soldier lethality through training realism. But when I was reading the specs, the engineering challenges to get that realism, they seem immense.
Well, they are, because the core requirement is right there in the name, trackless.
Which sounds simple, just, get rid of the rails.
Right, but if you don't have rails, where are these things driving?
Anywhere.
Anywhere. And that's the whole point. Legacy ranges are heavy on infrastructure. You need concrete pads, buried cables, all of it. The NGTT has to be deployable in, and this is their term, austere environments.
Austere is just military speak for the middle of nowhere.
Pretty much no cell towers, no power grid, just a field. And the specs for terrain transitability, that's where it can drive, are just brutal.
I was reading that it's not just pavement. They list loose dirt, loose sand, mud up to 2 inches deep.
Which is already tough for a small robot. Mud can be a real killer. But the one that I think keeps engineers up at night is the vegetation.
The grass.
The grass. The document says these robots have to move through grass up to 2 feet high.
2 feet. I mean, for a person, that's up to your knee. For a small robot.
It's a jungle. It's a complete visibility nightmare. If your robot uses LiDAR or cameras to navigate, 2-foot grass is a wall. It tangles in your axles.
But you have to have it.
You have to, because that's where the enemy hides. If your target can only drive on a perfectly trimmed lawn, you're not training for combat. You're right back in the carnival.
So the robot's mobility has to match the soldier's mobility. If I can walk there, the target needs to go there too.
Precisely.
So let's meet these robots. The Army wants 2 different kinds, right? An infantry one and a vehicle one.
Yep, the TMTI for infantry and the TMTV for vehicle.
Let's start with the infantry bot, the TMPI. What are we looking at?
Okay, so physically, you're looking at a ruggedized robotic platform, maybe 4 feet by 3 feet, low to the ground. And on top of that, you have a mannequin.
But a really specific mannequin. The doc calls for a realistic 3D human head and torso. It even specifies the exact shade of green.
Army standard green. But yeah, the look isn't the hard part. The durability is. This mannequin has to be a bullet sponge. The requirement is for it to survive 2,000 hits.
2,000?
2,000 hits from 7.62 millimeter rounds.
That's a serious round. That's like an AK-47 or a machine gun.
It's a lot of kinetic energy.
Right.
And the robot base itself has to be armored. It needs to take 3 hits in the exact same spot without penetration. You have to protect the brains, the motors. If a stray low shot kills the robot, the training stops.
Okay, so it's tough. But how does it move? This is where it got really interesting for me. Top speed is 10 miles per hour.
Which, doesn't sound that fast.
Right, I drive faster in a parking lot.
But for a human target running across a muddy, uneven field, 10 miles per hour is a pretty good sprint.
It's fast enough to be really hard to hit.
Especially since it can turn on a dime, a turning radius of just 10 feet. It can zigzag, it can go through 6 inches of water, climb a 10% grade, but the movement is just the start. The real leap is the behavior.
The smart reactions.
Yes. This is where it stops being just a target and becomes a simulator. The document talks about reactive behaviors.
I loved this section. The robot isn't passive. It has sensors that can tell when it's being shot at. And not just hits. It detects near misses.
Which changes everything. In the old system, you miss, nothing happens, you just shoot again. Here, if your round, subsonic, or supersonic passes nearby, the robot knows.
And it reacts.
It can be programmed to do what a person might do. It might stop, it might run faster, it might even reverse direction and run for cover.
It forces you to think tactically, not just aim.
Exactly. Is it running away? Do I chase? Is it charging me?
And there was that feature. The presentation device. I called it the bob.
The bob.
Yeah, the mannequin can lie flat to hide, right? And then pop up. But it can also do this thing where it bobs up and down when it's near missed.
That's a classic infantry tactic. You pop up, shoot, get back down, move, and pop up somewhere else. This robot can simulate that. It's designed to break a shooter's focus.
And just to make it even harder, these things have to work at night.
Full spectrum operations. The spec calls for thermal-enabled operations.
What does that mean exactly? Does it just have a light on it?
It's way more advanced. Modern soldiers use thermal sights that see heat. A cold plastic mannequin is invisible, so these robots need to generate their own heat, a thermal signature, so they glow in a scope, just like a warm body.
So you're in the dark, looking through your scope, you see this heat signature sprinting through the grass.
It creates stress, and stress is how you learn.
Okay, so that's the infantry robot, but there's also the vehicle robot, the TMTV, the big brother.
That's right. The TMTV carries a 3D silhouette of a tactical truck, usually made of plywood or something similar. And because it's a truck, it has to move like one.
Faster.
Much faster. Top speed jumps to 20 miles per hour, and the acceleration is key 0 to 20 in under 100 meters.
That requires some serious torque, especially on mud.
It does. And it's not just a moving billboard. It has its own presentation devices to simulate a driver and even a passenger.
So you can actually practice trying to hit the driver to stop the truck.
Precisely. And the sensors have to be smart enough to tell the difference.
It's not just hit or miss anymore.
Right. The system logs what you hit, that you hit the engine, the door panel, the driver. Hitting the door won't stop the truck. Hitting the engine will. It teaches tactical anatomy.
And to really crank up the pressure, the TMTV needs to have simulators for hostile fire.
Meaning it shoots back. It simulates shooting back. Flashes, bangs, maybe lasers that trigger the soldier's training gear. So you have a truck doing 20 miles per hour across a field, swerving and laying down suppression fire on you.
That sounds absolutely chaotic, which leads to my biggest question. You've got all these robots, infantry, and vehicle running around. How do they not crash into each other? Or worse, a soldier?
That is the multi-million-dollar question. It's all managed by what you could call the hive mind, a software system called TracheR2.
TracheR.
Catchy.
It's the conductor. Each robot is reporting its GPS position once a second, down to about 2 meters of accuracy. The control tower has a god's eye view.
But GPS can drift. It's not going to see a soldier lying in the weeds. Correct. Which is why obstacle avoidance is a top priority. It's listed as an objective capability. The robots need their own onboard brains to see and avoid trees, big rocks, and most importantly, humans and other robots.
Even if they're programmed to intersect.
Even then, the safety logic has to override the command. It has to figure out how to avoid a collision, much like self-driving cars.
Okay, but what if the software just freezes? What's a failsafe?
The big red button. The specs demand a physical remote emergency stop that's totally independent of the software. It's a hardware kill switch.
That's reassuring. Now, what about power? Are these things loud diesel engines?
Nope. Fully electric. The battery has to last for 3 hours of constant movement or 72 hours just sitting on standby.
That's a good long time. And charging.
Very versatile. They have to be able to plug into a normal wall outlet, both US and European voltages.
Which tells you they're planning on using these overseas.
Right. Or they can plug into the Army's tactical generators out in the field. They live out there.
But living out there means surviving the weather.
Oh, yeah. The environmental specs are basically a torture test. We're talking operating temps from minus 30 Celsius to 50 Celsius.
That's minus 22 Fahrenheit to 122. from the Arctic to the desert.
And storage down to -40. But that's the easy part. It's the rain, blowing sand, and the one they call salt fog.
Salt fog. That sounds awful for electronics.
It's a killer. It causes corrosion, shorts out circuit boards, they have to be sealed tight. And then there was the wind test.
The 35-mile-per-hour wind.
Right. The robot has to keep that big mannequin or truck silhouette standing upright in a 35-mile-per-hour wind.
Think about that. That silhouette is basically a sail.
It wants to tip over or fly away. The robot has to be constantly fighting that, which is a huge stability challenge.
It's like asking a waiter to carry a tray of drinks through a hurricane.
That's a great analogy, and it's why this isn't some hobby-grade RC car project.
Which brings us back to the business side. You said they're using a CSO, this commercial solutions opening. Why do that instead of a traditional 10-year defense contract?
Because they don't have 10 years. And frankly, a lot of the real innovation in this space is happening in the commercial world right now.
In automated tractors and things like that.
Exactly. The Army is basically saying, you've already solved tough navigation, you've solved battery life, can we just adapt your tech, paint it green, and put a mannequin on it?
So it's like Shark Tank for the Pentagon.
It really is. The first step, phase 0, is just a white paper. 10 pages or 20 slides, that's it.
A very low barrier to entry.
Very. If they like your idea, you move on. And then you get to phase 2, the pitch and demo.
The fun part.
You have to show up in person with your robot in a relevant environment, so a muddy field, and prove it can do what you say it can do. No PowerPoint can save you if your bot gets stuck in the grass.
And if you survive that, you get to negotiate a contract. It's so streamlined, it just shows how urgent this is for the Army.
They know there's a huge gap between the tech soldiers use in their daily lives and the tech they train on. That disconnect is a problem for readiness.
So if we step back from all the specs, what's the big takeaway? Why does it matter if a target has a brain?
It goes right back to that visualization we started with. If you train on predictable rails, you learn to game the system. You anticipate. But combat isn't a game.
Complacency kills.
Exactly. By making the targets unpredictable, reactive, and rugged, you force the soldier to actually think in real time. You force them through that whole decision-making cycle.
The OD loop. Observe, orient, decide, act.
Yes. If the target runs away, you have to decide now what to do. It changes training from simple shooting practice into a full-blown combat rehearsal.
It creates a thinking soldier, not just a shooting one.
And that is the definition of lethality thereafter.
Before we wrap, one thought kept nagging me from the obstacle avoidance section. These robots have to autonomously avoid hitting human soldiers on the range.
For safety, yeah, of course.
Right. But think about the tech needed for that. The robot has to see a human form, track its movement, predict its path, and then maneuver relative to that human.
I see where you're going with this.
If you just flip a single line of code in that software, if you change the command from avoid to pursue, you don't have a training target anymore.
You have a weapon.
You have a robotic wingman or a hunter.
The hardware is the same. The sensors, the motors, they're all identical. The only thing that separates a target running from you and a drone running at you is a parameter in the software.
We think of killer robots as this far-off sci-fi idea, but looking at these specs, the Army is essentially paying the commercial world to perfect the chassis and the brain for one right now.
It's a classic dual-use technology. Every step they take to make training more realistic also makes autonomous combat systems more viable. That line is getting very, very thin.
Something to think about the next time you see one of those little delivery bots rolling down the sidewalk.
Indeed.
That's it for this deep dive into the next generation trackless targets. Thanks for listening, and we'll catch you on the next one.